to see a chapter known as Newton's laws of motion. Before starting the main topic, we should know some common forces in mechanics, which are normal, friction, viscous, spring, tension string, and surface tension. Some of these forces we'll see. First is normal reaction. Suppose this is a block of mass m. It's put it on ground. So here is mg goes downwards and n goes upwards. Most important things to know about normal reaction is normal reaction is always perpendicular to contact surface. Perpendicular to contact surface. Second, we will see tension in string. Suppose this is a support. Here is a string and here is a block of mass m is attached. Here is a tension T in the string. So some important things to know about tension are tension can apply in both the direction like this, in both the direction. It always apply force towards itself. Tension in string is uniform at every point in massless string. These are some important points about tension in string. Some other forces we will see further. We will see further. Now we are moving to the next. That is Newton's laws of motion. Newton's first law say Newton's first law. Newton's first law is also called as law of equilibrium. First law says that if any body is at rest or in motion, it always want to remain in that position only. Unless any external unbalanced force act on it. In this case, F external is equals to 0. Then acceleration is also equals to 0. It means that F external is 0 and acceleration is 0. This is a balanced force. Although body is in rest or in motion, it does not mean that there is no force acting on it. There are some forces acting on it, but important thing is its resultant is 0. Newton's first law is also known as law of inertia. Inertia simply means that laziness. If any body is in rest or in motion, it always want to remain in that position only. Now, second law. In this law, F external is not equals to 0. In this law, new concept comes, that is momentum. We know that momentum is P equals to M into V. By the concept of momentum, we can conclude that more time, less force, more time, less force, and less time, more force. Momentum with respect to time, that is F equals to delta P upon delta T. By solving this, we get F equals to M into A. Now we will see third law. Newton's third law says that states that every action has equal and opposite reaction force. Some important things to know about third law are force always acts in pair, act at different bodies, and act at same instant. So third law says that action, reaction. Now we'll see free body diagram. Free body diagram is free body diagram. Free body diagram is that where forces are shown on the body, not by the body. Forces are shown on the body, not by the body, with the help of arrows. Body is shown as a point mass. In short, free body diagram shows reaction force on the body. Let's see an example. First, here is a block of mass M on ground. We know that a normal reaction goes upwards, perpendicular to contact surface, and mg goes downwards. So free body diagram of this will be by considering a point mass, and n goes upwards and mg downwards. If system is in equilibrium, then n equals to m into g. Now second example. Second example is on inclined plane. Suppose this is an inclined plane making an angle theta with horizontal. Suppose this is a block of mass m is put on it. Here is normal reaction acts perpendicular to contact surface here, and mg goes downwards. Uh, Acceleration will be in this direction. So by component divide, for mg, it is coming as a here mg cos theta, and here is a mg sin theta. By drawing free body diagram of this will be, and in this direction mg cos theta and mg sin theta in this direction. So acceleration will be in this direction. So by this we can conclude that n equals to mg cos theta and a equals to g sin theta. This is important. Acceleration is an important conclusion from inclined plane. Now we will see third example. That is string attached to a block of mass m. There is a tension T, and here is a mg downwards. So if a system is in equilibrium, then tension is coming as a mg. Three body diagram, T goes upwards and mg downwards. Next is a pulley. Here is a support. Here is a pulley attached. Here is a block of mass m2, and here is a block of mass m1. So free body diagram of m1 will be, for m1, tension upwards. String is 1, so tension will be same at every point. m1g downwards, and for m2 block, T goes upwards and m2g downwards. Now we will see applications of first law. Here is a one thing is remaining. Here is a pulley, and free body diagram of pulley will be tension in this direction also, T and T. So for staying it in equilibrium, here is a 2T is required. So now we will see application of first law. If a question is asked as a find tension string if a system is in equilibrium, then how to solve it? Okay, we'll see. So this is the question. Suppose a support, there is a support, and here is a string, here is a block of 5 kg, here is another string of here is attached 10 kg block. So this tension is T1 and this tension is T2. To draw a free body diagram of each for solving this. So free body diagram of 5 kg block will be tension in upward direction as a T1, and here is a 5g downwards, and as I already told you that tension it apply in both the directions, so T2 will be in the direction also. And free body diagram of 10 kg block will be T2 in upward direction and 10g in downward direction. And by solving or equating above this, we will get T1 equals to 150 Newton and T2 equals to 100 Newton. Now we will see values of tension and normal reaction on inclined plane. So yeah, suppose this is a inclined plane making angle theta with horizontal. Here is a support, here is a string, and here is a block is attached of mass m, and here is a tension T in the string. Normal reaction goes upwards. By component divided, it is coming as a, so mg downwards. By component divided, it is coming as mg cos theta, and here is a mg sin theta. So from this we get that here is a free body diagram T in this direction, n in this direction mg sin theta, and this direction mg cos theta. So from this we can conclude that n equals to mg cos theta and T equals to mg sin theta. These are some important conclusions from inclined plane. Now we will see application of second law. Application of Second law. Uh, we know that in this law, F external is not equals to 0. Here is a F equals to m into a. So from this acceleration is coming as a F net upon total mass. Let's say an example on this. Suppose this is a block of mass m. Here is a on ground. Here is force is applied in this direction like this. By so and this angle is theta. So we know that by component divided it is coming as a f cos theta and upward as a f sin theta. And upward normal direction is also goes upwards and mg downwards, and acceleration in this direction. So from this we get that f cos theta equals to m into a. From this we get a equals to f cos theta divided by total mass, that is m, and normal reaction will be n in this direction also and f sin theta in this direction also. So n is coming as a mg minus f sin theta. We find that acceleration in normal reaction. So second example, suppose this is a block of mass m1 and this is as a m2. Force is given it to it from this side as f. uh, it is on ground. So here will be n1, that is normal reaction, and for this block there is n2 from this side. Okay, acceleration will be in this direction. So big block m2 will give normal reaction to m1, that is n3. So free body diagram of m1 block will be, for m1 block will be f in this direction and 1 in upward direction, downward as a m1g, and here is a n3. So from this we get an acceleration is this direction. So from this we get f minus n3 equals to m1 into a. So now free body diagram of m2 block will be uh, n2 in about upward direction, downward as a m2g, and here is n3 normal reaction given to it by m1 block. Here is n3 acceleration in this direction. So from this we get, here is equation number 1, and from this we get n3 equals to m2a. This is the second equation. So by solving this we get that a equals to f upon m1 plus m2. This is a value of acceleration, and n is coming as a m2f upon m1 plus m2. Now we will see a system. What is a system exactly? Suppose this is a block of mass m1 put on the big block m2, and here is a string attached to another block, that is m3 having mass m3, and here is given to it force in this direction as a f. Acceleration of the system is in this direction. So now it is not easy to draw free body diagram of each. For making it easy, we consider all the blocks as a one system. How to solve it? By considering it all one system, then it will be coming as a all mass in one, that is m1 plus m2 plus m3, giving a force in this direction as a f, and acceleration is in this direction. So from this we get acceleration equals to f upon m1 plus m2 plus m3. Example on system. Suppose this is a example. Suppose this is a block of mass 1, and here is a block of mass 2, and here is a block of mass 3 kg. Force is given to it, that is 60 Newton in this direction. Acceleration will be in this direction. So by considering it as a system, it will be coming as a 3 plus 2 plus 1, that is 6, and 60 Newton in this direction, acceleration in this direction. So acceleration is coming as F net as 60 upon total mass, that is 6, is coming as a 10. So acceleration is 10 meter per second square. Okay, pulley system. Suppose this is a support, here is a pulley, and blocks are attached to pulley like this. So this is a big M and this is a small m. Situation is like this, m is bigger than small m. So acceleration will be in this direction. So free body diagram of small m will be tension in upward direction and mg is downward direction, and also acceleration in upward direction. By this we get T minus mg equals to m into a. This is equation number 1. And free body diagram of big mass m, that is tension in upward direction, and big mg downward, and acceleration is also in downward direction. So his equation is coming, that is mg minus t equals to m big M into a. Here's equation 1 and 2. By solving 1 and 2, we get acceleration as a equals to m minus m into g upon m plus m, and tension as a 2m into mg upon m plus m. These are important results from pulley system. Now, now we will see example on combination of pulley and inclined plane. Suppose this is an inclined plane making angle 30 degree with horizontal. There is a pulley attached. Here is a block of 3 kg. Here is a block of mass 6 kg. So tension in string is T. We consider it as a system. So 9 will become of mass, and here is a 30 Newton, that is this 3g equals to 30, and this will be mg sine theta by component divide, and it is coming as a 30. So here is also 30, here is also 30. So block will not move. Acceleration is equals to 0. For finding tension, we have to suppose this block 3 and 30 Newton downward and upward T. System is in equilibrium, so tension equals to 30 Newton. Now, pulley trick. Pulley trick. Here is this pulley trick is only valid for moving pulley. Suppose this is a pulley, velocity v1. Here is the velocity v2, and here is the velocity of vc. Then what is the vc? Vc is the average of these two velocities, that is v1 plus v2 upon 2. This is a pulley trick. But the important thing is velocities must be in one direction only. Okay. Now we will see constraint motion. Constraint motion part 1. Suppose this is from before starting the example, we should know when if pulley moves x, then string release to x. This is important. So now we will see example on constant motion. Suppose this is a support. Here is a pulley attached like this. Here is a block A is attached, and here is another pulley. Here is fixed, and here is a block B is attached like this. So when we move this pulley X downwards, then this block will be moves upward as a 2x. If a pulley moves X, then string releases 2x, because this is a fixed. So Now next example, on inclined plane, this is a theta. This is a pulley fixed, and here is a another pulley is also here is a fixed. So this is a block B, and here is a block A is attached like this. So uh, when pulley moves upwards and as x by 2, then this block will move in this direction as a x. Now let's see new concept, that is heavy rod. Heavy rod. Uh, Heavy rod means that string having mass. Suppose this is a support. Here is a string having mass. Here is a block of mass m is attached like this, and here will be mg downwards, and here is a point A, here is a point B, and here is point C. So tension at point A is equals to mg simply, and tension at point B is equals to m plus small m by 2. Sorry, this is a string having mass m. So this tension at B is equals to m plus m by 2 into g, and tension at C is equals to m plus small m. Tension at C is equals to g. And important thing to noted here is a T A is less than TB. Tension at A is smaller than tension at B is also smaller than tension at C. This is a condition. So next we will see Lambis theorem. Lambis theorem. So here is a, suppose here is force F2, and in this direction as F3, and in this direction as F1. Here is angle C, and here is angle B. Sorry, A, and here is angle B. We can also draw this like this. F3 in this direction, F1, that is F1 is in this direction, and downward, that is this as a F2. This angle will be B, this angle will be A, and this angle will be C. So Lambis theorem says that F1 upon sine A, that's opposite angle for this. F1 upon sine A is equals to F2 upon sine B, and is equals to F3 upon sine C. This is a Lambis theorem conclusion. So now we will see apparent weight in an elevator. Apparent weight in elevator. So this is a three conditions are there. Suppose this is a elevator. The man is standing here, and this condition, three cases are there. This acceleration, this elevator is not moving when acceleration is equals to 0. This is moving upwards with acceleration A, and this is moving downwards with acceleration A. Here is normal reaction upwards, and here is mg downwards. So acceleration is 0, because acceleration is 0, and n equals to mg, simply n equals to mg in this case. Second case is that, second case, here is n goes upwards, that is normal reaction, and mg downwards. So from this we get that n equals to mg plus a, and in this case n equals to mg minus a. Normally we can see that while going up with an elevator, we feel our weight is increasing, but how mathematically this is proof. And in this case also, while going downwards in an elevator, then we feel our weight is decreasing. Okay, now spring force. Difference in string and spring is that string is string is extensible, and while spring is extensible. String transmit force while spring transmit as well as stores force, and string is only pulling force while spring is pulling and pushing, both are force. So this, suppose this is a spring like this is a normal condition, and this is a we stretch the string with x distance. uh, this is the original and this is a after stretching. So the x distance stretch here. So spring force generated here. So fs equals to formula is fs equals to minus k delta x, where k is a spring constant and delta x is change in position of spring. Now we will see cutting of spring and string or string. Uh, Suppose this is a support for, here is string for block of mass m, and here is a spring attached to another block m. Here is here is b and here is a point a. So this condition is in equilibrium. So this is downwards coming as mg, upwards as fs, that is spring force, that is coming as mg also. Here is a gravitational force of this block will be mg, and spring force also equals to mg. So mg, then tension in this string will be 2 mg. This is in equilibrium condition. If we suppose this is a spring, now we have to cut this string. So after cutting, immediately it becomes 0. The tension in this string will be 0. So free body diagram of this block, that is a and b. So free body diagram of a will be uh, this is 0. So mg, that is free spring force, and mg also downwards. So acceleration in this case is coming as a 2g. And so suppose in second case we cut this, this is not cut in this case. So in third case we cut this. Then free body diagram of this block will be, that is a, coming as a, in this case when string is not cut, when string is cut, then free body diagram of block of mass m will b will be uh, fs, that is mg upwards and mg downwards. So mg get cancelled. The acceleration is 0 in this case. Now we cut constant. Now we see this is denoted by k. So spring constant is inversely proportional to length, where length is l is length of spring. uh, we take an example on this. Suppose this is a spring, uh, and question is asked as a spring is cut in 3/5 ratio. Then what is spring constant in this? So 3/5, 3/5. So length, it is coming as a, this side is coming as a 3l by 8, 5 plus 3 8, and it is coming as a 5l by 8. So spring constant is inversely proportional to length. So the spring constant will be 8 by 3k, and 8 by, this is coming as 8 by 5 e. Now we will see combination of spring. First is parallel combination. Suppose this is a attached support. Here is a spring. Here is another spring like parallelly, and here are attached to one block. This is a K1 and this is a K2. Then K equivalent in this case is K1 plus K2, and second is series combination. And in this, suppose these are two springs attached to one block M. Here is a K1, here is a K2. Then K equivalent, that is 1 upon K equivalent, equals to 1 upon K1 plus 1 upon K2. This is a result of a series combination. Now we will see frame of references. Frame of references. Frame of references are divided into two parts, that are non-inertial and non-inertial frame of references. First is inertial frame of reference. In this, observer is at rest or moving with a constant velocity. Example: a car is traveling at a constant speed, or a body at a rest. Now, second is non-inertial. Non-inertial frame of reference. In this, observer is accelerating with some acceleration. Example: lift goes up or down with acceleration of, or second example, body is rotating. Suppose for understanding this, we consider an example. Suppose this is a elevator. Here is mass of here is a block of mass M is put, and here is a person standing here, and this is person B, and here is a observer A. Observer A. Then observer A is elevator is accelerating in upward direction, and observer A will observe that in normal direction in this direction and mg downwards. So observer A, the free body diagram of this block with respect to A will be n upwards, and acceleration is also in upwards, and mg downwards. So person observer A will say that n equals to mg plus A, and observer B will say that he's also accelerating, so he considered as a is a 0. So he observed that uh, here's a n and here's a mg. Acceleration is a 0 for this person. So for this person, n equals to mg. But this is a wrong, and observer A is a right, because observer A is a inertial frame of reference, and observer B is a non-inertial frame of reference. For overcoming the non-inertial problems, so we introduced a new concept, that is pseudo force. Pseudo force. Pseudo force is used for converting non-inertial frame of reference into inertial frame of reference. Now, so how pseudo force works? That is non-inertial frame of reference plus pseudo force gives inertial frame. Pseudo force is equals to m into a. But the direction of pseudo force will be opposite to acceleration of reference. So in this example, with the help of pseudo force, this person is observing that a equals to 0, but this is wrong, we know. For overcoming this problem, pseudo force, that is m into a, gives in this direction. So it is also coming as a n equals to mg plus a. So this problem is solved with the help of pseudo force. Now we will see constraint motion part 2. Constraint motion 2. There are three cases. First is, suppose this is a big block of mass m, and here is a pulley attached to another small block of mass m, and here is a string. Suppose this string is moved with velocity v, then the velocity of this block will be also v, in this direction v, and this will be move in upward direction as a V. Then second case, suppose this is a block of mass bm and here is a pulley. This string is attached now. Then here is a block of mass m. So this big m is moved with velocity v in this direction. So what is the velocity of this block? Then it will be v in this direction and v in this direction also. Then it is coming as a v equals to vi cap plus v j cap. Now third case is a combination of both. So here is a big block of mass m, here is a pulley, and here is a small block attached. And so this is not attached now. So we string, both the string and block are moved with velocity v. So this is moved with velocity v in this direction and this is a v in this direction. So what is the velocity of this block? Then it will be uh, v in this direction and v in this direction. So it is coming as a v plus v 2v, then 2v upward and v in this direction. So it is coming as a v I cap plus 2v j cap. Now on inclined plane, constant motion, that is inclined plane, for this we have to divide component of resultant velocity in direction of constraint. Suppose we take an example. Suppose this is a support, here is a pulley, and this moved with this is attached to this block like this, and here is our surface. This string is pulled with 2 meter per second velocity, and obviously it will be 2 meter per second. And what is the velocity of this block? It's a question. So by component divide it is a v in this. By component divide for v, then it is coming as a uh, v r radial velocity and vt in this direction. So we know that by component divide, suppose this is angle theta, then it is coming as v cos theta. By this we can say that vr equals to v cos theta. Then we know that vr, that is this is 2 meter per second, and 2 equals to v, and cos so this angle is 60 degrees, so this is 60 degree. Then v cos 60 is equals to 1 upon 2. Then velocity is coming as a 4 meter per second. This block will move in 4 meter per second. Now सर 1 मिनट टाइम कितना हुआ है? Second example, suppose this is a support and here is a scale like this, and it is moved with velocity. It is moved in this direction, and this will be in this direction. It is a moving like this. So by this is a point A and this is a point B. So this is a velocity VA, and this is VB. Then by component divide, it is coming as a so this is V. Then it is coming as VA R, and this is coming as a VA T. That is tangential. So this is by component divide for this. It is coming as a VBT, and this is coming as VBR. For it is coming as VB cos theta by component divide. This is angle theta, and this is coming as a VA sin theta when this angle is a theta. When VBR is equals to VAR, then this scale will move like this. So VAR equals to VBR. Then VAR is a V VA sine theta, and it's coming as VB cos theta, that is VBR. And by this we get VB equals to VA sine upon cos tan theta. VB equals to VA tan theta. So now we will see impulse. A impulse is a very large force for a very small interval of time. That implies less time and more force. We know that force is a rate of change of momentum with respect to time. That is F equals to delta P upon delta T. So by this we get that F into delta T equals to delta P. This is a conclusion. So here is a delta P is a constant. Uh, area under force versus time area under force versus time graph gives momentum. Impulse is a momentum changed in very less time. Impulse is a momentum changed in very less time. If force are not constant, if force are not, this is a for constant. Now if force is not constant, then delta P equals to integration of F dt. If force are not constant. uh, Thank you.